I'm going to go ahead and share my screen. All right. So, can everyone see the screen? It says limits day 1. Yes, okay, cool, thank you. All right, so on Monday, on our very first day of Calc 1, we began our journey by looking at graphs. And specifically, we spent a lot of time looking at graphs where pictures were a little bit weirder than what they used to be, meaning that they had holes or they sort of skipped from one point to another point, okay? And so maybe as a quick sort of check-in before we move on, we didn't answer all of these what's new questions. And so I wonder if we can take a moment, look at this graph, okay? And see if we can answer those 3 questions under what's new. So what is the limit as x approaches -3 of f of x? What is the limit as x approaches 0 of f of x? And what is the limit as x approaches 3 of f of x? Okay, so take a moment, get back into looking at pictures and finding these answers from pictures. We'll check those, and then we will move on with some different strategies. Okay, so let's take maybe about a minute or so. All right. So let's take a look at that first question, the limit as x approaches -3. Now, based on this graph, what do we think that answer is? What is that limit as x gets really close to -3? Okay, I see a -3.5. I see a 0. I see a bunch of zeros. No imposter O's, just zeros. Okay. So folks who found 0, what were you looking for on your graph? Right? Because it's one thing to be able to get an answer, but it's another thing to know why you got that answer. All right, so someone says, looking at where x equals -3, what is the y value there, right? And you're looking at that x-axis, exactly. And so if we think about it, we're looking right here, right? That's where x equals -3. And when we look there, the y value is 0. Okay, so that's how we get that answer. All right, what about that second question? As x approaches 0. So as x approaches 0. You see 0.5, 1/2, 0.5, 0.5. Okay. And if we were to apply that same reasoning, we're going to where x equals 0, right? X is 0, not where y is 0. We're looking for where x is 0. And that looks to be about 1/2, somewhere in there. Okay. All right. And our last question here is, we actually did on Monday the limit as x approaches 3. And we said that as we get close to 3, the y value actually got really, really close to 1, okay? And so when we look at these numbers, we really want to keep in mind that the numbers represent the y value that the graph is getting really close to, okay? So for the purple one, does the y value at -3 also equal 0? Okay, so let's go back to that first question. Does the y value at x equals -3 also equal 0? Yeah. So this happens to equal f of 0. I mean, f of -3. Okay. Now, what about that lime green point? Does the function actually get to 1/2 at x equals 0? Yeah. So we could say that this equals f of 0. Okay. Last question, that pink point, does the graph get to a y value at 1 at x equals 3? No. Okay, so we would say this is not equal to f of 3. Okay. And so that's planting some seeds for sort of the second half of class when we talk about continuity. All right, that's going to be a big theme for the second half of class is what does it mean for a function to be continuous? All right. And so we're going to use this notation later, and we are going to come back to the graphs. But for right now, let's sort of move along. Okay. So on Monday, we did a Desmos activity. And we wrote down some concepts that we thought about, some questions. And I think the biggest takeaway here is this last underlined sentence, which is that when we're looking at limits, we're zooming in on a really small part of the graph. And we're describing what happens there. Okay, so we're getting as close to the point that we're interested in as possible. And we're saying what's happening around there. And this fancy equation here is nothing more than a shorter way of saying, find me that y value that the function gets really close to as x approaches a certain value, okay? So we did a couple questions where we looked at some pictures, right? We looked at the pictures. From the pictures, we could see what was happening from the left, from the right, from both sides, all right? And then we started very briefly taking a look at how do we find it if we don't have a picture, right? That's where we left off class. How do we find limits if we do not have a picture? And it turns out that our first strategy here, which is one that we should always try to start with, is just plug the number in, see what happens, right? Because the idea is that most points on a graph are not going to be weird. A few of them are going to be weird. You might have a hole here, a discontinuity there, other weird things happening, but most of the graph is going to be made up of points where you plug in an x value, you get a y value out, okay? So our focus for today is going to be this. What happens when we plug in our number and something weird happens, okay? So I hope you had your coffee this morning or your tea, whatever beverage works for you, but things are going to get a little weird, all right? So let's start. Let's start a look at number 5. And it says the limit as x approaches 1 of x squared minus 1 over x minus 1 equals. And so the first thing I'm going to do is say, let's plug in 1. Okay, let's plug in 1. Let's see what happens. So I get 1 squared minus 1 over 1 minus 1. And 1 squared is 1, so we get 1 minus 1 on the top, which is 0, and 1 minus 1 on the bottom, which is 0. Okay. Very well played. Right? That is very problematic for us, okay? But I want to be a little bit more specific here. It's problematic for 2 reasons. The first reason is that pesky 0 in the denominator. That is problematic, okay? If you type something into your calculator, you say 5 divided by 0, your calculator is going to say you have an error. Or you type 10 divided by 0, that's going to be a problem. You type in 1 over 0, that's going to be a problem, okay? But the problem we encounter when we get a 0 over 0, right? So the 0 on the top and the 0 on the bottom. There's a fancy name for this problem. Okay. So when we get a 0 over 0, we call that the indeterminate form, okay? And what that means is that we have to figure out how to find that value, all right? But we can't do it by just plugging in the number. And so what we want to think about too is we're going to zoom back in our brains to either when you took pre-calculus or when you took Math 116 with the STEM core group, all right? So you're rewinding in your brain, let's say all the way back to late September for the STEM core group, okay? And we spent like a whole chapter on these weird functions we called rational functions. And at the time I was like, oh, like I want you to practice your factoring. Let's see what happens. And we sort of drew these graphs, but this is a point where we kind of get to come full circle, okay? So when we get 0 over 0, one strategy that I'm going to ask you to try is factor. Now, on the notes, I've laid that out. I said, here, I want you to factor. On the quizzes or on the exams, it's going to be much less directive. So it's going to be really important that we recognize when we use factoring versus when we use some of the other strategies we learn, okay? But let's take a look at this for a moment. So we get 0 over 0, that's a problem. So let's kind of come back to here. And we're going to rewrite that first part, the limit as x approaches 1. And I'm going to keep the denominator the way it is, x minus 1. And let's factor that numerator, x squared minus 1. What does that give us when we factor? Yeah, x plus 1, x minus 1, okay? Now, for those of you that this is like, yes, I really know how to factor that, that's awesome, all right? And if you're like, oh, I still need to like think about it a little bit more, that's also fine, okay? So I don't want to say like, oh, just because you got the answer first, it means that, you know, you totally get it, but factoring is going to be a skill that we use in this unit, okay? And so we can factor that x plus 1 and, oh shoot, I have one of those on the top. I also have one of those on the bottom, okay? Now, in general, if I had a common factor on the top and the bottom, I could go ahead and cancel those, right? So let's say I had 2 divided by 2. Well, that gives me 1, right? I have -5 divided by -5. I get 1. So when I have an x minus 1 on the top and an x minus 1 on the bottom, algebraically, I can say, let's reduce those, okay? Now, once I reduce those, let's see what we're left with. The limit as x approaches 1 of what's left. Just that x plus 1. Exactly. Now, what was that strategy I said that we should always try first? Plug in or substitution, right? So we've done a little bit of algebra. Let's try plugging in the number again, okay? So everywhere I see an x, I'm putting a 1. 1 plus 1 gives us 2, right? Now, can you believe that a question that looked like this, the limit as x approaches 1 of x squared minus 1 over x minus 1 came down to 1 plus 1 equals 2, right? That seems almost a little disheartening in some senses because you're like, I just did all that work and it's really just 1 plus 1 equals 2, okay? But two things here. When I have a common factor on the top and on the bottom, the ones that I canceled out, does anyone remember from pre-calculus, what does that look like on a graph when I have that common factor on the top and the bottom? Okay, so I want to go back here for a moment and just write something that is when x minus 1 equals 0. We have a hole in the graph, okay? Now, some people call it a hole, some people call it a discontinuity, interchangeable, okay? But if we pull up the graph of this, which we'll do in a little bit, and I graph x squared minus 1 over x minus 1, and I zoom in at x equals 1, there's going to be a hole in the function, okay? Would people like to take my word for it, or would we like to see that picture right now? Where are we at? Let's see that picture. Okay, hold on. Let me. All right. Desmos, such an amazing tool. Okay, such an amazing tool. So let's graph our picture. So y equals x squared minus 1, that's in my numerator, divided by x minus 1. Looks like a line, right? But let's get really close to where x equals 1. Okay, so x equals 1 is here. So if you like having a slider, like a point that you can kind of move around, where did it go? There it is. Let's keep it between negative 0.5 and 1.5. Okay. So I'm going to move this point, right? So I'm getting closer and closer to an x value of 1. So remember, x equals 1 is right here. So we want to see, like, what is the y value getting really close to? And I think we can even see just from the graph that y value at 0.9 is 1.9, right? Now, the y value at 1.1 is 2.1. So 1.9 and 2.1, we get pretty close to, oh, okay. So 1 comma undefined means that this graph has a hole at x equals 1. So that's why when we plugged in the number, we got 0 over 0, okay? But a limit doesn't care if you actually get there or not. I just care when I say find the limit, I just care like, what does it get really close to? So let's scooch back a little bit. Looks like it's getting really close to a y value of 2, okay? So when we think about what a limit is asking us, we're saying, what does it get really close to? That's all we're doing, okay? Yeah, so I saw a question in the chat on line 2. So one of the things you could do in Desmos, and you don't have to do this, but if I want a point to come up, right, I can type a comma f of a. Now, f is defined by my function over here. So it means that I'm going to put an a value in, and then I'm going to put that into the function, and that will give me the y value. You can add a slider, so that way you can sort of slide the point along and see what's happening. But those are sort of like fancy things. You don't have to do that, okay? But all this does is define a point for you. So if we hide those, whoops. If we hide those, we get our original graph, okay? But when we reduced it, we actually got what? G of x equals x plus 1 is what we got when we reduced it. So check this out. The red graph, the purple graph, the red graph, the purple graph. They look like they're the same, don't they? Okay. But let's go on the purple graph to x equals 1. You see how that says 1 comma 2? Our reduced form, all it does is fill in that hole. It fills in the hole, so now we can find the value that was there. Okay, the value that was there that we plucked out, made it a hole, and threw it away. Okay, so when we're finding all of our limit stuff, that's what we're doing. We're saying, there's a hole in this function. How do I patch it back in so I can sort of find the value that was there? Okay. Okay. So does that help kind of clarify what we're doing when we're factoring and canceling some terms out? Yeah. Okay. So when you're going through the quizzes, I would really encourage you to kind of graph it and see what happens. Because if you graph it, you'll know what your answer is supposed to be, right? So it's like a built-in check that you can say, all right, well, maybe I'm not so confident about my algebra, but while I sort of get used to that, I can start to think, how can I check my answer, right? And maybe it's just a question of remembering how to factor or whatever else it might be, okay? All right, so let's try another example, okay? So we have the limit as x approaches -3. Now, first thing that I want to see you do is plug in -3, okay? So -3 squared plus 3 times -3 over -3 squared minus -3 minus 12. And that's going to give us 9 minus 9 over 12. Whoops. 9 plus 3 minus 12. Oh, man. I got that indeterminate form again. Okay. Because I have the indeterminate form, we're going to try going back. And in this case, we're going to try factoring. Okay. So the limit as x approaches -3. All right, let's hopefully our brains are a little bit warmed up right now. What is the numerator of this when we factor it? We have x squared plus 3x. What do we get when we factor that?
X parentheses x plus 3.
All right, and when we factor that denominator, we'll get x minus 4 and x plus 3. There's that common factor, right? That common factor is the problem, because this factor tells us that when x plus 3 when x plus 3 equals 0, we have a hole in the graph. Okay. Now, specifically though, where is the hole? X equals what? X equals -3. Okay, so at x equals -3, there's a hole. And guess what the question is asking us for? It's asking us for the y value at the hole. So that's why we can't find it, right? We can't find the y value there, but we can cancel out our factors, try substitution again, and I bet we'll get the answer. Okay, so let's get rid of those factors. We get the limit as x approaches -3, and what's remaining? X over x minus 4. Okay. Let's try plugging in our numbers now. -3 over -3 minus 4, which is -3 over -7, which gives us 3 over 7. Okay. So show me first why substitution does not work, right? Show me why substitution doesn't work. Though the reason why I'm being particular about this is because sometimes substitution is literally the strategy, and we get so overwhelmed with all these other types of strategies that we kind of forget about it. Okay, so if you think about some of these quiz questions, some of them you can do substitution, some of them you're going to need to use factor. Okay, so if you tried some of those quiz 1 questions and you were like, I'm getting 0 over 0, I don't know what to do with that, this is what you can do with that. Okay. All right, let me pause here for a moment. Any questions so far? Okay. So let's do this. Let's give you a moment to try, and here, let me leave this one up on the screen too. I'll give you a moment to try example number 7 on your own. Okay, if you haven't already. I have a sneaking suspicion some of you have already been working ahead, which is totally fine, but let's see what happens with question number 7, and then we will summarize with how do we know we're gonna need factoring, okay? Okay. So no matter how far you've gotten, hopefully we've plugged in -1. We've seen that that gives us a problem. And so now we need to try a different strategy. Okay. Now, if you're a little rusty on the factoring, I would encourage you to find some problems out there, practice the factoring. Okay. But here's sort of a quick hint. So x is getting to -1, right? X is getting to -1, and that's causing us to have a problem. My guess is that there's going to be a hole at x equals -1, which is why there's a problem, right? But if there's a hole at x equals -1, that must mean that there's a factor on the bottom and a factor on the top that make that hole happen. Does that make sense? Like how we had the x plus 3 and the x plus 3, and we were able to cancel those out, and that was the same place as where the hole was. If you're not super confident on the factoring, at least you know one of the factors, right? Then you can kind of like figure out what might multiply to get the term you're looking for, okay? So that's sort of a back end way if you're like, I don't feel super great about the factoring. But what we get in that denominator then is x plus 1 times x minus 3 should give us x squared minus 2x minus 3. Okay. And then if we think about the top, we're going to need 2x plus 1 to make that equal 2x squared plus 3x plus 1. Okay. Now, even though I'm not spending time in class talking about factoring, you are 100% welcome to come to office hours and say, hey, I just need a review of factoring. Okay, that is absolutely fine. All right, so we get rid of that common factor. We get the limit as x approaches -1 of 2x plus 1 over x minus 3. We try substitution again. And we do indeed get 1/4. Okay. So let me zoom in for a moment so we can see all three questions on the same page. All right. Now, seeing all three of these questions together, I think helps give us an idea of maybe the pattern or the flow to these kinds of questions. All right. But does anyone have any clarifying questions about any of the steps that we took or any of the steps we didn't take? Where did numbers come from? Where did they go before we move on? Well, does anyone have any, oh, sorry, clarifying. Is the hole still there in the questions? Do we have to write that part in the blue? Okay, the hole is still there. The hole is in the original function. Okay, so the hole is still there. But in order to find the y value, we have to sort of like pretend patch it in. That's why we factor and we reduce. Okay, that's like a band-aid for that hole so that we can sort of find the y value that was supposed to be there. Do you have to write this part in the blue? Absolutely not. Okay, you do not have to write that part in the blue. I think it's sort of useful to consider like, why are we doing that? But you don't have to write it. Okay. Yeah, we're just sort of like rewriting the function in a way that will help us see what we want to see, right? And sometimes we do that by making it more complicated, and sometimes we do that by making it more simple. Yeah, exactly. Okay. So the question I want you to kind of think about, but we're not going to answer right now, is how do I know when to use factor? That is the question that you want to have an answer to. Okay. How do you know when to use factor? Right. And so we'll come back and think about those answers together in a class later. But before then, let's kind of talk about some other cases where when we plug in our number, we encounter a problem. Okay. All right. So case 3. If we take a look at these 3 examples, all right, you'll notice that in example 8, 9, and 10, they all have radicals. All right. So because they have radicals, it doesn't mean that we're always going to encounter a problem. We should always, always, always still try substitution first. Okay. So let's try substitution. Let's see what happens. 4 minus 3 times 4 plus 4 over 4 minus 4. Let's see, 4 minus the square root of 16 over 4 minus 4. Now that's going to give me, oh shoot, that indeterminate form. Okay, so indeterminate does not mean it can only happen with like an x squared thing. Indeterminate form can happen anytime. The part that makes it indeterminate is you get a 0 over 0. Okay, so this is a problem for us. Now, our strategy here is going to be a different strategy. Okay, because when we see radicals, it's not as easy to factor. Okay, but when we see radicals, we're going to make this a lot messier before it gets better. Okay, so all I'm doing right now is copying down my original problem. Okay, now we're going to multiply by 1. Okay, we're going to multiply by 1. And this is going to be like the fanciest 1 you ever did see. Okay. Oh, yes. All right. So numerator or denominator, which one has the radical?
Numerator.
The numerator has the radical, right? Okay. So whatever is the one with the radical, the fancy way that we're going to say 1 is we're going to multiply by the conjugate. Okay. So the conjugate, if I had like x plus the square root of 2, what is the conjugate of that? Exactly x minus root 2. Okay. And if I had x minus 2 root 5, what is the conjugate of that? Okay. Now, what about this? What is the conjugate of that? Good. Okay. So when we find the conjugate, the thing we are changing is the plus. If it's a plus in between, it becomes a minus. If it was a minus in between, it becomes a plus. And if it was a minus in between, it becomes a plus. Okay, but we don't change anything else. We don't change any of the other signs. It's just the one between the x and the radical. Okay, and so Thea, thinking ahead to how this might apply to our question down here, the conjugate of our numerator is x plus square root of 3x plus 4. I know you didn't mean that 3. Okay, so x plus the root of 3x plus 4. Now, this thing that we're writing, this whole fraction that we're writing is supposed to be the fanciest way of saying 1, right? Everything in here is supposed to say 1. And the way I've written it right now, it does not say 1. It says x plus root of 3x plus 4. So in order to make it 1, I have to have the same term on the bottom. Okay, now I have 1, and now I have not changed my question. Okay. All right. Now that decision-making process is important. It is also important to be able to do all the algebra we're going to do right now. Okay. So the limit as x approaches 4. Okay. I'm going to ask you folks a favor, okay? And this favor is really a favor for you. So I'm highlighting this, not because it's in the denominator, but I'm highlighting it because it does not have complex conjugates, right? Like the top has an x minus and an x plus. The bottom does not. Do not multiply if there is not a pair of conjugates, okay? Sometimes that's going to be on the bottom. Sometimes that's going to be on the top in a different problem, okay? But the key here is do not multiply if there's not a pair of conjugates. You will make your life so hard, and all of a sudden your problem will look like a bazillion times worse and it will never get better, okay? So just trust me on that one. Do not multiply that part out, but we will multiply out the top, okay? So because I'm not multiplying out the bottom, I'm just gonna write that again, okay? Now we're gonna multiply out the numerator though. The numerator is where we have a pair of conjugates. That's what I'm going to multiply. Green, because we're good to go to multiply. Okay, so Thea, that's what I mean by pair. You have a pair of conjugates. Conjugates comes in twos, right? So wherever the conjugate pair is, that's where I need to multiply. Does that make sense?
Do you mean like one quantity has like an x minus and one has an x plus?
Yeah.
Oh, okay. Thanks. Sorry.
Oh, you're fine. We're using so much language. Okay. So now we multiply out. Okay. So I have I have an x and an x that multiplies to give me x squared. Now I'm only going to write this out the first time, okay? I will not write this out in all the other problems, and if you don't need to write this out, that's totally fine. But let's just go through the idea. I multiplied my first terms. I'm going to multiply the outer terms, so x times root 3x plus 4. Now, I know that's weird, right? That we get x times square root of 3x plus 4. Part of the game of Math 150 is be confident enough to write it down, even if you don't know where it's going to go. Okay, so I don't know what x times root 3x plus 4 is, but I'm just going to write it down. Now, when I write down when I multiply the inner terms, I get negative x square root of 3x plus 4. When I multiply out the last terms, I get negative root 3x plus 4 times root 3x plus 4. So let me pause here for a moment. Okay, so the bottom we said do not multiply this out. So that's why this looks exactly the same as it did in the previous step. But before we start canceling or simplifying, does anyone have any questions about where the numerator came from?
So you just multiplied everything that was like the radical, like both radicals together?
Hmm?
Okay.
Yeah, I just did FOIL. So my first terms times my outer terms times my inner terms times my last term. It just looks weird because I have square roots. Okay. Does that clarify your question?
Yes, thank you.
Are you sure?
um yeah, I think so.
Okay. All right. So what can we do from here?
I feel like you could probably factor out the x on the numerator where it says x squared plus x root 3x plus 4. That way you can get something similar to the denominator.
Yeah, I thought that we could certainly. So for those of you who don't see what she's talking about in these first two terms, I could factor out an x. That's definitely possible. Okay. What else could we do?
I was thinking we could simplify the numerator.
Okay, simplify how?
Like Eric said, there's like terms, and then there's also if you combine. Oh no, that's the only like term. Yeah.
Okay, so in specifically, which terms are we combining?
X times the square root of 3x plus 4, and minus x times the square root of 3x plus 4.
Okay.
They cancel each other out.
Okay, so let's move our blue parentheses to here, okay? And as gross as these terms look, I have a plus something and a minus that same something, right? I have that plus something, minus something. They're going to go away, right? It doesn't matter how complicated they are. That still is going to go to 0. Okay. All right. Now, Thea, let's see. You said the x root 3x. Exactly. Okay. Now, what else can we simplify, specifically in this last pair of terms that I'm multiplying? What can we do about this? Okay, so the root 3x plus 4 and the root 3x plus 4 should simplify to 3x plus 4. So what we get in the numerator is we have x squared. That was that very first term that we didn't do anything to. This one, okay? The next two terms went to 0, and then this last term, something times itself, became 3x plus 4. Just that something, no square root. Okay. All right. From here, we got a few more steps. Okay, now this one is a tough problem. That's why I wanted to start with this one. All right, this one is probably the hardest of sort of these complex conjugate problems. Okay, but let's keep going. The limit as x approaches 4. On the top, I get x squared minus 3x plus or minus 4. Minus, good. Okay, over my numerator or my denominator. Ooh, sorry. Okay. I'm going to go ahead and factor the numerator. The limit as x approaches 4. I factor, I get x minus 4, x plus 1. Same denominator that I have not changed the entire time. Okay. All right, do we see this x minus 4 term on the top and then this 4 minus x on the bottom? All right, we got an x minus 4 on the top and a 4 minus x on the bottom. Wow, it would have been so nice if they were the same. Like they were both x minus 4 or they were both 4 minus x, right? But they're not. But they're close. And interestingly enough, they are close enough, actually. I would say that is not that far, okay? It turns out that when you see like an x minus 4 and a 4 minus x, they are the same, except one of them is multiplied by a negative 1. Okay? In other words, negative 1 times 4 minus x will give me x minus 4. That's really nice because now I can redo. I have a -1 that I didn't have before, so I need to make sure I don't lose that. But if you have a case where it's like x minus a number and that number minus x, they are so close, they're almost the same factor, except one of them has been multiplied by -1. Okay. All right. Let's see what happens now if we try and plug in 4. Okay. So -1 times 4 plus 1 over 4 plus 3 times 4 plus 4. My numerator is going to be -5. My denominator is going to be 4 plus square root of 16. And so we get -5/8. Okay. So that is a substantial problem to start off with. All right. We're going to use pieces of this. Specifically, the conjugate piece, that thing in the purple, that really fancy one, we're going to use that a lot. Okay. We're going to use the idea that we multiply out the conjugate pair, but the part of the fraction that is not a conjugate pair, we're going to leave that alone. And the reason we're going to leave that alone is because it should cancel with something else at some other point. And if we multiply it out, we're going to lose sight of that, and then we're not going to be able to cancel anything. Okay. Natalia, that -1 is a -1 times 4 minus x is another way of writing x minus 4. I didn't factor, like I didn't just multiply by -1. Okay, so you could think of x minus 4. I split it into -1 times 4 minus x. Okay.
So you kind of just rewrote it in a different way.
Mm-hmm.
Okay.
I know that it can feel very intimidating when someone's like, trust me, these tricks are going to come in handy, right? Now, I've done like a bazillion of these problems. So like I've made my fair share of mistakes, and I've learned the hard way that if I multiply out something that I don't need to, it might actually cause me more problems later on, right? So I don't expect you to know all these little like, oh, I should try this here, or I should try this here. But I wanted to do this problem because I think it highlights a lot of the common strategies that come up, okay? All right. All right, so 2 comments in the chat. It might make more sense if you pretend you factored out that -1. Exactly. So that -x plus 4, we can write it as 4 minus x. All right. So Eric, I think that's a great point. Gloria's point, should we write the limit as x approaches 4 all the time? Yes. Yes, until you plug in the number. Okay. Yes, until you plug in the number. Okay. All right. Before we go on break, I'm going to talk through example 7. Okay. Because I think example 6, again, it was like sort of like a fire hose to the face. Like, here we go with conjugates. But I think number 7 will be maybe a little bit more highlighting the important decision-making pieces. Okay. All right. So let's do number 9, and then we'll go on a break. So number 9, like all the other ones, I'm going to plug in 9 and see what happens. So I plug in 9, I get square root of 9 minus 3 over 9 minus 9. I get 0 over 0. That is that indeterminate case. Okay. So Indeterminate case means I need to think of a strategy. I could try factoring. That actually works for this one. So for those of you who are pretty good with your factoring, you can absolutely factor this one, okay? But if we want to highlight this complex conjugate strategy, it might look something like this. The limit as x approaches 9, square root of x minus 3 over x minus 9 times the fanciest way of saying 1. Okay? How should we write 1 in this case so that it's beneficial for us? Root x plus 3. Absolutely, absolutely. Okay? Now, why are we getting that negative, like a negative root x minus 3? Where is that negative coming from?
Professor, sorry to interrupt. I just had a quick question. So on that last example, number 9, when you factored out the -1, shouldn't the top be x plus 4? Like a positive x, or no? X plus 4?
Well,
Or is that
it came from something that was positive, right? Like
okay?
x
The-
minus 2. So if I keep it a positive after I factored out a -1,
There's that factor doesn't give you 4 minus x, right? Or sorry, no, okay. I understand. Okay, I see.
Okay.
I thought they were yeah, no, I see it. Okay.
Yeah, so -1 times 4 minus x, I distribute, I get -4 plus x, which is x minus 2.
I thought I just fed someone bad info. Okay, I see it. All right, thank you.
All right, where are folks getting this negative root x though in question number 9? I'm a little concerned about that negative. I would see a mix of answers. Am I still really quiet? I feel like my sound is all the way out. I'm also talking extra loud. I'm so sorry, folks. Thanks for your patience.
I think it might be fixed if you're wearing headphones, because if you're using the speakers, it's actively trying to cancel our sound and also hear you. So it's canceling you out as well.
Was that a problem last semester?
I don't think so. Or maybe it might help if, Moonly, if you mute yourself back again. I think you forgot yourself unmuted.
Okay. How does it sound now? Does that sound better? Okay. Well, should we pause right now then? Should I see if I can fix this, take our break now, and then we can finish example 9 when we come back? Okay. Oh, is this better now? Okay, well, let's finish example 9 then. Okay. Thank you, folks. That would be the worst. Okay, so when we are looking for the conjugate here, okay, we just want to change the sign that is in between. So all these ones up here at the top, when we had the yellow, oh, maybe, yeah, maybe. Okay, so all these things where we had the yellow, that's where we changed the sign, right? We changed the sign in between the term and the radical, like the radical term and the non-radical term. And so if we apply that to example 9, we should end up with square root of x instead of -3 plus 3. Okay. If I only do that there, I'm going to have created an entirely different problem. So I want to make sure I also refer to that on the bottom, square root of x plus 3. Okay. Now, when I multiply, when I combine these together, root x minus 3, root x plus 3, x minus 9, root x plus 3. Let's look at the numerator. Should I color the numerator green or red? Like green, I'm going to FOIL it out. I'm going to multiply it out, or red, don't touch it. Yeah, exactly. We are going to multiply. And now why are we multiplying the numerator and not the denominator? Exactly, okay? The numerator has the conjugate pair. The denominator does not. So don't touch that. Something should cancel at the end there, okay? All right. Now, when we multiply the numerator, what do we get? I'll give you a moment to work that out, but when we multiply the numerator, what do we get? I see 2x minus 9, right? So those first two terms, square root of x times square root of x, gives you x. What happened to the inner and outer terms? Yeah, they canceled out, okay? So the inner and outer terms, they cancel out, and I get x minus 9, okay? Well, check this out. I'm so glad I didn't multiply because I have an x minus 9 on the top. I have an x minus 9 on the bottom. What's left in our expression? Yes, yes. Okay. 1 over, right? That's the important part. 1 over square root of x plus 3. Okay, that square root of x is still there. That square root of x plus 3, it's still there, but it is in the bottom of the fraction. So even after you cancel things, it better be in the bottom of your fraction. Okay. Now, let's plug in our number again, see what happens. 1 over square root of 9 plus 3, 1 over 6. Okay. We were able to patch the hole, so to speak, see what it looked like when we patched that hole. So the 1 over 6 is the y value the function gets really, really close to when x gets close to 9. Okay. So at the end of the day, remember, that's what we're looking for. That number at the end represents a y value. The number we put in represents an x value. Okay. All right. So Now seems like a good time for a break. Feel like a lot of brains are quite full out there. Those are definitely some juicy problems. But when we come back, we're going to take a look at one more type of question. Okay, one more type of question where we plug in numbers and we get an indeterminate form, and how do we handle that last case? All right. And then after that, we'll have time to do a little Desmos activity and summarize some things for limits day 2. Okay. So folks, it is just about 10:50 right now. If you could be back at 11 a.m., I will see you back then. All right, how do I know when to use the conjugates? Okay, so how do I know when I should factor versus how do I know when I should use conjugates? And which conjugate do I use? Okay, so these are questions to think about as you're trying the problems. How do you know when to do what? Okay. So on that note, let's move on to this last case, which is case 4, complex fraction. All right. And so yes, like many things that we learned in the past, all of it kind of comes back and we're expected to not just know it and remember it, but to use it in the context of a different problem. Okay. And so let's take a look at example 11 here, okay? So I'm taking a look at number 11. My first step, as always, is to plug in the number that they want and see if it works or not, okay? So 1 over 1 plus 1 minus 1/2. I think we can all kind of tell that's going to give us a 0 on the top over 1 minus 1. And there is our 0 on the bottom. So 0 over 0 means we have an indeterminate form and it is problematic, okay? So we need a strategy. We've learned factoring, we've learned complex conjugates, but this doesn't look like one that we could factor. It doesn't necessarily look like one that conjugates, like with radicals, might be helpful. And so our goal here in that then is to think about all the tricks we know with fraction, okay? And so I'm gonna rewrite this from the get-go so it doesn't look, I think it looks a little less overwhelming this way, okay? I'm gonna take the numerator and I'm going to write it here. Okay, that's my numerator. And then I'm going to take the denominator and I'm going to write it here. Okay, so I've just sort of split it into 2 sets of fractions, like the numerator and the denominator. And what do I put in the numerator for that second fraction? A 1, exactly. Okay, and so the reason I'm doing this is just because sometimes when we work with fractions, we have like a fraction on the top and a fraction on the bottom and then another fraction somewhere else, and it's just really hard to keep track of all the lines. Okay, and so one thing I do to kind of avoid this is sort of split into top and bottom, and then I'm able to focus on each individual part. Okay, so right now let's think about if I want to combine the 2 fractions that are in the yellow, 1 over x plus 1 minus 1/2. How do I do that? How do I subtract those 2 fractions in the yellow?
Common denominator.
Got it, common denominator, right? Some of you are probably like, why is she asking that question? But it's good for us to remember these little things along the way, right? So in order to combine the 2 fractions in the yellow, we want a common denominator. And so we can say 2 times 2 over that minus x plus 1 over x plus 1. Okay, so all I did was multiply the first fraction by 2 over 2 and the second fraction by x plus 1 over x plus 1. And all of this is multiplying by fancy ways of saying 1, but in a way that's going to allow us to simplify. All right, let's combine those two fractions in the yellow. We'll get 2 times x plus 1 on the bottom. That's my common denominator. And then in the numerator, I get one minus x. Any questions about where the 1 minus x came from? So if you simplify that numerator here, you get 2 minus, what do you get when you distribute that negative 1? Okay. So you get negative x and then minus 1. Okay. So these are examples of steps that you might want to show. You can certainly do them off to the side, but I would encourage you to sort of like show more work than you think you need to show, especially like in an exam situation. You just want to make sure you don't make any silly mistakes somewhere along the way. And sometimes just by writing it, you're like, okay, it is getting smaller. It is getting more simple, right? Instead of just being so overwhelmed with the beginning part. All right, so we get 1 minus x in that numerator. All right. Anyone see a structure that we saw in a previous problem that we can use to our benefit here? All right, so someone has typed in the chat 1 minus x and the x minus 1. I think we chose like a green color for that earlier, right? This one, 1 minus x, and this one, x minus 1, when I cancel them, I don't get 1. Like when I reduce them, I don't get 1. But when I reduce them, I get negative 1. Okay. So this and this reduce to give a negative 1. We'll end up with the limit as x approaches 1 of negative 1 over 2 times x plus 1. Now, let's try plugging in our number. Okay. Questions on number 11? Okay, why is that a negative 1? So a step that we showed in the other problem was when we had something like 1 minus x, we can think about what happens if we factor out a negative 1. Okay, so what am I left with if I factor out a negative 1? Well, I get negative 1 plus x, right? And another way I could write that is negative 1 times x minus 1. And so then, Richard, this x minus 1 will cancel with that x minus 1. And then we'll still have that negative 1 factor on the top. Okay. Yes, exactly. I know negative 1 plus x is the same as x minus 1. Exactly. Okay, cool. The reason why I put this little algebraic trick in 2 of the problems is because this little structure helps a lot. Because sometimes you're looking to cancel factors and you're like, so close, but I cannot, they're not exactly the same. But in this case, they're just off by a factor of negative 1. Okay. So good trick to kind of keep in that back pocket. All right. Let's take a look at example number 12. Okay, so let's just do one more example here where we're looking at this idea of complex fractions. And like number 13 here, I will do that question. I will show all the work for that before I post my notes. Okay, so you'll have something to check for that if you want to do that on your own time. Okay. All right, so example 12. Let's plug in our negative 3. Let's see what happens. 1 over negative 3 plus 2 plus 1 over negative 3 plus 3. Nothing special here. We get in that indeterminate form, 0 over 0. Okay, so we have to figure out another way to approach this problem. Now, did people like this idea of splitting into like the yellow and then the orange pieces? Was that helpful visually? Okay, so I'm going to do the same thing here where the numerator, I'm just going to write over in the first fraction, 1 over x plus 2 plus 1. Right? That's enough fractions in that parentheses to deal with. And then what do I write in the second parentheses? Good. 1 over the denominator. Eric, that's a great question. And yes, it would. There's actually a lot of different types of indeterminate forms. In Calc 1, we only do one. In Calc 2, you'll learn about 3 or 4 other ones. And so this is the one we're learning right now, but there are certainly other cases to consider. Okay. I know, exciting things to look forward to, right?
Professor, quick question on that, follow-up. Then are we expected to see anything like that on the tests or quizzes that you give us? The other forms?
It is possible that we will see a number over 0. We're going to do that case next week.
Okay, so you are going to go over it. Okay, never mind then.
Yeah.
All right, thank you.
Some of the other ones, in case you're curious, is if you look up things that are like infinity to the 0, like that's another kind of indeterminate case. So there's a few others that tend to come up in the, but we save those for Calc 2, okay? But if you're curious, you can take a look at others. And then for the other ones, there are different strategies to apply. Okay, so back to this one. Now, with the yellow part in this one, I'm going to use the same idea that I did in the previous question with the yellow part, which is I have two fractions. I want to make them into a single fraction, so I'm going to need a common denominator, okay? So the limit as x approaches -3, I'm going to end up with 1 plus x plus 2 all over x plus 2. So there's my original denominator, and this is my numerator and denominator. I just created a common denominator of x plus 2, okay? All right, let's start to clean this up and see what we get here. So my new numerator is now going to be x plus 3, because 1 plus x plus 2 is x plus 3. That is fantastic, because my denominator now has two parts, x plus 2 and x plus 3. Right? This is that orange piece. This one is from the bottom of the yellow fraction, and this is from the top of the yellow fraction. But what's beautiful about this, it goes back to that idea of factoring. I factor so that I can reduce. Okay. Now, limit as x approaches -3, I only have to plug it in to 1 over x plus 2. And that will give me 1 over -3 plus 2, or -1. So I'll give you a moment to copy that down. Put both questions up on the screen so we can kind of see the parallels between what's happening. Right? This is actually exactly what we did in 116. Yes, exactly, Yitan. This is exactly what we did in 116 or 141, depending on which class you came from. But this all goes back to how do we find that coordinate of that point of discontinuity, right? That's what this question is asking, okay? All right. So again, I will do example 13 in the notes before I post them, okay? So you'll have another question with worked out answers so you can kind of practice on your own. But again, this question that I'm asking at the bottom, how do I know when to use complex fractions? I really want us to think about how do I know when to use which strategy, okay? Without that piece, without that decision-making piece, you'll get to a test and be like, I don't know, they all like, how do I know which one to use? Okay, so practice that decision making. Even just like go to the textbook and look at problems and talk about them with each other. Okay, I think we should use conjugates here. I think we should use factoring. I think we should use this. You don't have to do them, but I think practicing making that decision is actually incredibly helpful. Okay. All right. So we're going to switch gears a little bit. I'm going to stop sharing my window for a moment. I'm actually going to